Hello everyone, I am Rudrani Korchaudhuri and I am a PhD student at Presidency University, India, and they are my collaborators. So today I'll be talking about one of my research work which is simulating X-ray emission in the galaxy clusters that host active galactic nuclei. This is a brief outline of my talk. First of all, I'll explain what are active galactic nuclei and their feedback. Then I'll be talking about some of the observational signatures of AGN feedback on its ambient gas. After that, I'll briefly introduce the simulation that has been used in our work. Finally, I'll show you some of our results, and after that, I'll compare our result with the actual observation, and finally I will summarize. So what are active galactic nuclei? We know that most of the galaxies in our universe harbor a central supermassive black hole. Some of them are active and they accrete material from their surroundings. This class of supermassive black holes are known as active galactic nuclei. Due to the accretion, they radiate energy and sometimes they are so bright that they outshine the entire host galaxy. A fraction of this radiated energy, gets coupled to the surrounding media. This phenomenon is called AGN feedback. Here in this image you can see this bright spot. This is actually the central AGN and this is the jet or the energy radiation coming out of the central engine. Now the effect of AGN feedback is clearly seen from the X-ray observations of galaxy clusters. We know that galaxy clusters are the largest gravitationally bound objects in the universe and they are also the large reservoirs of the hot gas emitting in X-rays. Now, in a phenomenal work by McNamara and Nelson 2007, they have shown two X-ray underluminous regions around the central AGN. This was believed to be occurred due to the AGN feedback activity which displaced the hot X-ray emitting gas in the neighborhood of the AGN, creating these X-ray cavities. Okay, so in this work we have tried to make the synthetic observation of the Chandra X-ray telescope starting from the cosmological simulation data. In order to study the effect of AGN feedback on the ambient medium and compare our work with the actual observation. So we started our work with the cosmological simulation data, which is for our case is gauge simulation. Then we have modeled the X-ray emission from the simulated galaxy clusters using the astrophysical plasma emission code APIC. Finally, we have created the synthetic X-ray observation of the Chandra X-ray telescope using a ray tracing simulator, namely MARCS. Now, I'll explain all these three blocks individually throughout my talk. So, for our work, we have used the Gadget simulation. This is a cosmological hydrodynamic simulation. So, it contains gas physics, dark matter dynamics, and radiative cooling. It also considers star formation and supernova feedback, and a self-consistent treatment of the growth and the associated feedback from AGN. Now for the purpose of our work, we have used two sets of simulation, one ran by DiMatteo et al. 2008 and another by Khandai et al. 2015. This is a simulation snapshot from the DiMatteo et al. 2008 and this is a simulation snapshot by Khandai et al. 2015. Now these are the basic parameters of the simulation that we have been using in our work. Here you can see that Khandai et al. Have used a box which is bigger in size. This is 100 megaparsec and also the number of particles are very large. But DiMatteo et al. Used a box for their simulation. Uh, a small box for the simulation, also the number of particles are smaller. Also, starting from a high redshift, K15 was performed all the way up to the current epoch, while the D08 simulation were ran up to only the redshift 1. Now, the main reason to use this small box size D08 simulation is that it contains both the scenario in their simulation in which AGN feedback is present and absent, while K15 does not have a companion simulation in which AGN feedback is absent in their simulation. Now, in order to study the effect of AGN feedback on their surrounding medium, we want to compare it with a scenario in which AGN feedback is absent. For this purpose, we have used both the with and without feedback simulation of D08. We then model the X-ray emission from our simulated galaxy clusters using a plasma code called APIC. These are two X-ray maps, theoretical X-ray maps of the hot gas using APIC around 2 AGN at redshift 1 in the K15 simulation. Here the color bar shows the X-ray flux in arcs per centimeter square per second. So the more red means the more X-ray flux coming out from those regions, and bluer means the lesser X-ray flux. Okay. Then finally we have performed the synthetic X-ray observation using the photon simulator MARCS. MARCS is a ray tracing simulator which can simulate the detailed and realistic observation of various types of astronomical sources with Chandra telescope. It takes into account all the phases that a photon undergoes from incident on the telescope mirror to its detection by the detector. So these are two synthetic photon maps around the same AGN as I have shown in the earlier slide within the same region. These two are the 200 kilosecond synthetic observation in the soft X-ray band, that is 0.5 to 2 keV. Here the color bar represents the photon number count. Now these are only two example maps that I have shown so far. But in order to study the effect of AGN feedback statistically, we need to consider all the AGNs in our simulation box. So we have modeled the X-ray emission around around all the AGNs in a region of 50 kiloparsec, 50 cross 50 kiloparsec, and we have also made the synthetic observation in that region as well, and we have stacked the theoretical X-ray maps and the synthetic X-ray maps. And then we obtained the stacked surface brightness profiles from the stacked maps. Now look at the left panel shows the stacked radial profile of the X-ray of the theoretical X-ray flux. Here the blue represents the radial profile of the X-ray flux when the AGN feedback is absent in the simulation. The red dashed represents the radial profile in the presence of AGN feedback. Now if you look at the right panel, and only the blue dots and the red diamonds, this represents the synthetic radial profile in the presence and absence of AGN feedback. The blue represents the absence of AGN feedback, and the red represents the stacked radial profile of the synthetic X-ray emission when the AGN feedback is present. Now if you compare these two panels, if you look at these two panels, you will see that at this central region, the X-ray flux is always lowered when in the presence of AGN feedback. Uh, and this holds true for the theoretical profiles as well as the X-ray synthetic X-ray observation. Finally, we have compared our work with the actual observation actual observational data. For this purpose, we have compared our work with the work of Mukherjee et al. 2019. Here the black dots and the green dots represents the actual observational work of Mukherjee et al. 2019. The black represents the normal galaxy in which the AGN is not present, and the green represents the galaxies for which AGN is present. Now you can see that the actual observation also shows the lower X-ray flux at the central region in case of the AGN host galaxies. So we can conclude that our work agrees well with the actual observation of actual observation of Mukherjee et al. 2019, and we are seeing a lower X-ray flux at the center in presence of AGN feedback. So to summarize, we have modeled the X-ray emission by coupling our highest resolution cosmological simulation with a plasma code APEC, and then we have performed the synthetic Chandra observation of the X-ray emission from a large statistics of simulated galaxy clusters. We have found a central deficit of the X-ray flux in the presence of AGN feedback obtained statistically, and our results show good agreement with the actual observation. So, thank you.